Welcome to the deep dive.
Oh,
Okay, so today we're really getting into something significant. Stephen Hawking's A Brief History of Time.
yeah, it's definitely a landmark. A book that, well, it's somehow managed to take these incredibly complex ideas about the universe and make them, accessible, something people could actually talk about.
Right, and you have to wonder why it hit so hard, don't you? Was it just that he explained it well, or was it tapping into something deeper, like our basic need to figure out where we fit in the cosmos?
I think that's a big part of it. And for this deep dive, we're using the Wikipedia page on the book as our guide,
Yeah.
sort of distilling the key points.
Exactly. Think of it as the core essence of Hawking's work. And our goal really is to unpack those core ideas, maybe find some surprising insights, and just make it fascinating for you, hopefully sparking some, aha moments along the way.
Okay, so A Brief History of Time. It came out in 1988, Stephen Hawking. And like you said, the crucial thing was it wasn't for physicists. He deliberately wrote it in, well, non-technical language.
Which is pretty amazing considering what he was trying to cover. I mean, the whole
Well, it
story of the
was.
universe, right? Its structure, its
Mm.
origin,
How it developed, what its fate might be. It's incredibly ambitious.
and he dives straight into the big concepts: space, time, quarks, gravity, the fundamentals.
And he cleverly brings together the two kind of main pillars of modern physics. You've got general relativity,
Einstein's big picture view of gravity and the universe.
exactly, and then quantum mechanics, which is all about the weirdness at the tiny subatomic level. They describe the same universe, but, well, they don't always play nicely together.
It's like different languages almost. And underlying all of it was this massive goal, wasn't it? The search for a unified
The
theory.
theory of everything,
Yeah.
yeah. Trying to tie all those forces and particles into one neat package. The ambition is just staggering.
And people clearly responded to that ambition. I mean, this book wasn't just popular, it was a phenomenon. What was it? Over 25 million copies.
25 million and
Yeah?
translated into like 40 languages. It's hard to overstate the impact.
You have to ask, what was the key thing that grabbed people? Was it just the sheer scale or time or black holes maybe?
I think it was partly the clarity,
Yeah.
tackling these massive questions, but also making you feel like you could understand them. And Time magazine naming it one of the 100 best nonfiction books.
Yeah.
That speaks volumes.
Its influence really spread out too, didn't it? There was that documentary film in 91,
Right. Brought the visuals to it.
and then the abridged versions, illustrated ones, I think even a CD-ROM.
Huh. Yeah, definitely dates it a bit.
Yeah.
But it shows how they were trying to reach people in different ways. And apparently there was even talk of an opera based on it.
An opera. Wow. That really shows how much it crossed over from science into, well, general culture. Okay, let's talk about how it actually got published. Hawking went to Cambridge University Press in 83
And it's interesting, the editor, Simon Mitten, he was apparently a bit worried.
about the equations.
Yeah. He thought too many equations would, put off the general readers Hawking wanted to connect with.
The famous warning, right? That every equation could have the readership. That's quite a stark way to put it.
It is. And Hawking clearly listened. He mentions it, which is why the book basically has just that one equation.
EMC.
EMCC. A brilliant move, really, focusing on the concepts over the math for that audience. Though you could ask, did simplifying it that much lose anything important?
Possibly. And the first edition, it had that introduction by Carl Sagan, didn't it? With that amazing story about Hawking signing the Royal Society book.
Right after Isaac Newton's signature. Yeah, that's such a powerful image, placing him directly in that line of scientific giants.
But then that intro got removed later. Something about copyright.
Yeah, a little behind-the-scenes publishing detail.
Ah.
Remind you that even these huge scientific works have practical hurdles. Okay, shall we dive into the chapters? Chapter 1, Our Picture of the Universe.
And it starts so perfectly with that anecdote.
The triple.
Yes. The flat earth on a giant tortoise and then turtles all the way down. It just instantly shows how far our ideas have evolved from those, well, charming but simple explanations.
It's a great hook. And then he walks us through the history. Aristotle thinking the Earth was a sphere, but, the center of everything. Ptolemy building on that geocentric idea.
Until Copernicus flips it, puts the sun in the middle, then Galileo seeing Jupiter's moons through his telescope, which was huge, Kepler figuring out the planets move in ellipses.
And Newton tying it all together with universal gravitation. It's a whirlwind tour, but it sets the stage beautifully. How our view of our place has kept changing.
He also touches on that ancient debate, didn't he? Did the universe always exist like Aristotle thought, or was there a specific creation moment?
Right, the philosophical versus theological views.
But the big shift came with the discovery that the universe is expanding. That pointed towards the beginning, didn't it? Some incredibly hot, dense state billions of years ago.
Yeah, the seeds of the Big Bang idea are right there, even if it's not fully fleshed out yet.
And then that quote he includes. An expanding universe does not preclude a creator, but it does place limits on when he might have carried out his job. That really makes you think, doesn't it?
It does. It shows how science can frame those philosophical questions differently, even if it doesn't answer the why. Okay, chapter 2. Space and time.
The real fundamentals. And again, he starts with the history, how ideas changed. Aristotle's view that things naturally want to be at rest.
Yeah, and the old idea that heavy things fall faster, which Galileo famously showed wasn't true.
Right, and Galileo's work leads into Newton's laws, but Newton's ideas had this radical consequence. No absolute space, no absolute rest, it's all relative.
A huge conceptual leap.
Yeah.
But then, even the idea of absolute time started to wobble.
The assumption that time just ticks along the same for everyone, everywhere.
Turns out, not quite true, especially when you get near the speed of light. Ole Romer first showed light had a finite speed watching Jupiter's moons.
And then Maxwell's equations for electricity and magnetism actually predicted the speed of light. Amazing. Which led people to think about the ether, right? The stuff light supposedly travels through.
The luminiferous ether, yeah. But the Michelson-Morley experiment famously failed to find it.
Which was a crucial piece of the puzzle. It suggested the speed of light is constant no matter how you're moving.
And that's the bedrock for Einstein's special relativity in 1905. Constant light speed, same laws of physics for everyone moving uniformly, and bam, out comes E myself.
And the idea that space and time aren't separate anymore.
Exactly. They're woven together into this four-dimensional thing, space-time, mind-bending stuff.
Seriously. And then, just 10 years later, 1915, Einstein drops general relativity.
Which changes everything again. Gravity isn't a force pulling things, it's the curvature of space-time caused by mass and energy. And this theory inherently points to a dynamic universe, one that's changing.
So yeah, in just 2 chapters, we've gone from Earth at the center, static universe, to this dynamic four-dimensional space-time shaped by gravity. It's quite a journey.
Definitely. Chapter 3 then zooms in on the expanding universe, building the case for that dynamism. How did we even figure out how far away stars are?
He talks about that. People like William Herschel mapping the sky, and then Edwin Hubble using those Cepheid variable stars.
The pulsating stars.
Yeah, like cosmic lighthouses. Their brightness pattern tells you their true luminosity, so you can figure out the distance.
Clever. And Hubble used that in the 1920s to measure distances to other galaxies.
And made that incredible discovery in 1929, redshift. The light from most galaxies is shifted towards the red, and the farther away they are, the bigger the shift.
The smoking gun for an expanding universe. Things are moving away from us, and the farther they are, the faster they're receding.
It was so revolutionary, even Einstein wasn't initially comfortable with it, right? He'd put in that cosmological constant to keep his model static.
His greatest blunder, he supposedly called it later.
No.
But others, like Alexander Friedman back in 1922, had already used Einstein's own theory to predict an expanding universe, assuming it was, roughly the same everywhere.
Homogeneous and isotropic.
Right. And then, decades later, totally by accident, Penzias and Wilson at Bell Labs find this faint background microwave hiss.
The cosmic microwave background, the afterglow of the Big Bang.
Exactly. Which people like Dick and Peebles were actually predicting theoretically around the same time. It was this perfect convergence of theory and unexpected observation.
Amazing moment in science. And then there's the work on singularities.
Roger Penrose showed collapsing stars could form points of infinite density, and that led him and Hawking to suggest the universe itself might have started from a singularity.
Although it notes Hawking later modified that view, thinking about quantum effects, which just shows how science evolves, doesn't it?
Absolutely. Nothing is set in stone. But the expanding universe idea became central. Okay, chapter 4, the uncertainty principle. Big shift here, down to the quantum level.
Yeah, he starts with that old idea of scientific determinism, Laplace's demon, right? If you knew everything perfectly now, you could predict the future perfectly.
The clockwork universe. Very neat, very tidy. But then physics started hitting problems, like the ultraviolet catastrophe. Classical physics predicted infinite energy from hot objects, which, well, obviously doesn't happen.
Enter Max Planck and his quantum idea. Energy comes in little packets, quanta.
A revolutionary concept.
Yeah.
And that paved the way for Heisenberg's uncertainty principle.
Which says you fundamentally can't know both a particle's exact position and its exact momentum or speed at the same time. The more you know about one,
The less you know about the other. It's not just about our measuring tools. It's built into reality. So there's this inherent fuzziness. How does that mess with our everyday intuition?
completely. It introduces probability right at the heart of things. It totally undermines that old deterministic view.
Which led to the whole framework of quantum mechanics. Heisenberg, Schrödinger, Dirac, incredibly successful, even if Einstein famously disliked its probabilistic nature.
God does not play dice.
But it seems maybe he does, or at least the universe does. Hawking also explains wave-particle duality here.
The idea that things like light or even electrons can act like waves sometimes and particles other times, like the two-slit experiment shows.
Yeah, it's deeply weird, but experimentally verified. He mentions Feynman's sum over histories as one way to try and picture it.
And then the big problem. General relativity works for gravity, and the large scale quantum mechanics works for the small scale, but they don't fit together, especially at singularities where gravity is extreme.
Right. Finding a theory of quantum gravity that unites them is, well, arguably the biggest challenge in fundamental physics today.
Chapter 5 then drills down into the elementary particles and forces of nature, the building blocks.
Again, he gives us the history. From Aristotle's elements, earth, air, fire, water.
To Democritus thinking about atoms, Dalton, and molecules, then discovering the electron, the nucleus, the neutron.
And finally getting down to quarks. Gell-Mann's idea. And not just one kind.
No. Up, down, strange, charm, bottom, top, and they've color too, red, green, blue.
It's just terminology for a quantum property, not actual color. But yeah, it's a complex picture. Plus, antiquarks. Though there aren't many of those around now, thanks to the early universe conditions.
He then gets into particle spin, fermions and bosons.
Right. Fermions are the matter particles, electrons, quarks. They have half-integer spin, and crucially, they obey the Pauli exclusion principle.
Which basically means no two fermions can be in the exact same state at the same time. That's why matter takes up space.
Exactly. It's fundamental to structure. Bosons, on the other hand, have integer spins and don't obey the exclusion principle. These are the force carriers.
So photons carrying electromagnetism, W and Z, bosons for the weak nuclear force.
Gluons for the strong nuclear force holding quarks together inside protons and neutrons, and the hypothetical graviton for gravity.
He mentions color confinement, too, the idea that you can't pull quarks or gluons out on their own.
Correct. They're always stuck together in composite particles, hadrons, like trying to isolate one pole of a magnet, kind of.
And then the idea of unification, like how the electromagnetic and weak forces merge at high energies. The electroweak force.
Yes. And the hope for grand unified theories, or GUTs, that would maybe unite the strong force with that too, still searching for that.
It's all about finding that underlying simplicity, isn't it? Okay, chapter 6. Black holes. Everyone loves black holes.
They are definitely captivating. Regions where gravity is just overwhelmingly strong, nothing gets out.
Not even light. The term itself came from John Wheeler in '69, but the idea is older.
Yeah, John Mendelsohn back in the 1700s speculated about stars so massive light couldn't escape. Pretty prescient.
Hawking explains how stars normally balance gravity with the outward pressure from nuclear fusion.
But when they run out of fuel, gravity wins. They collapse. Could end up as a white dwarf, held up by electron pressure, or a neutron star, held up by neutron pressure.
But there's a limit, right? The Chandrasekhar limit.
About 1.4 times the sun's mass.
Wow.
Above that, nothing known can stop the collapse. It just keeps going.
Forming a black hole. And the boundary is the event horizon.
The point of no return. Hawking uses that Dante quote, "All hope abandon, ye who enter here." Pretty stark.
He talks about different types, rotating versus non-rotating, and how he started finding evidence for them, quasars, pulsars.
And especially X-rays coming from systems where gas from a normal star is falling onto an unseen massive companion, like Cygnus X1.
Which became a prime candidate, and led to that famous bet between Hawking and Kip Thorne.
Right. Hawking initially bet against it being a black hole, but later conceded when the evidence piled up. Shows his scientific integrity.
Definitely. Which leads perfectly into chapter 7. Black holes ain't so black. This is Hawking's own groundbreaking stuff.
Yeah, this was revolutionary in the 70s. The standard view was black holes only grow, nothing escapes. They seem like perfect absorbers, kind of like endpoints for entropy for disorder.
But Hawking and Jacob Bekenstein, too, started thinking differently. They proposed the area of the event horizon is actually a measure of the black hole's entropy.
And if it has entropy, it must have a temperature. It might be incredibly tiny, but it's not absolute zero. And if it has a
It
temperature,
has to radiate.
exactly.
Mm.
Black holes aren't perfectly black. They emit radiation, Hawking radiation. It completely changed the game. Think about that. The ultimate cosmic vacuum cleaner actually leaks.
How did he explain it? Something with quantum mechanics near the edge.
Virtual particles. The vacuum of space isn't empty. Particle-antiparticle pairs pop into existence and annihilate constantly. Near an event horizon, one might fall in while the other escapes.
And the escaping one carries energy away from the black hole.
Precisely. Taking a tiny bit of the black hole's mass with it. So, over unimaginable timescales, black holes actually shrink and theoretically evaporate completely.
Wow. So these cosmic monsters aren't eternal after all. That's incredible.
It's an amazing connection between gravity, quantum mechanics, and thermodynamics. Truly profound work.
Okay, Chapter 8 brings us back to the biggest picture, the origin and fate of the universe. Revisiting the Big Bang. There's that anecdote in the Wikipedia entry about the Vatican Conference.
Oh yeah, where Pope John Paul II supposedly told the scientists it was okay to study the universe after the Big Bang, but not the moment itself, because that was, creation.
And Hawking's quiet thought that, well, his own talk was about how there might not have been a distinct beginning in the way the Pope meant, if space-time is finite but boundless. He even compared it to Galileo's situation.
It does highlight that potential friction between scientific models and some religious interpretations.
So he talks about the early universe being incredibly hot and dense, no structures possible, and reminds us about Gamow predicting that leftover heat.
The cosmic microwave background found by Penzias and Wilson. Huge evidence for the Big Bang.
Right, and the Big Bang also explains why there's so much hydrogen and helium around, with heavier stuff cooked up in stars later. He lays out the main evidence. Redshift, the CMB, element abundances. Solid case.
But puzzles remained. Like, why is the universe so incredibly uniform on large scales? The horizon problem. How did distant regions, which seemingly couldn't have communicated early on, end up at the same temperature?
And Alan Guth's idea of cosmic inflation comes in here, the incredibly brief, super rapid expansion right at the beginning.
Yeah, inflation could potentially smooth things out, solve the horizon problem, and explain other features too. It's become a standard part of the model, though the details are still debated.
Hawking also discusses the fine-tuning problem, how the universe's constants and expansion rate seem, well, just right for life.
If they were slightly different, maybe stars wouldn't form, or the universe would collapse too quickly or expand too fast for structures to form.
Which leads to the anthropic principle. Maybe we see the universe this way because, well, if it were different, we wouldn't be here to see it.
A controversial but thought-provoking idea. And then there's Hawking's own no-boundary proposal.
The idea that if you use imaginary time, mathematically, the universe could be finite, like the surface of the Earth, but have no edge or starting point.
Exactly. No initial singularity needed. Just a self-contained, finite space-time. A very elegant, if abstract, concept.
Chapter 9 tackles the arrow of time. Why does time seem to flow only one way?
He identifies 3 arrows. Thermodynamic, things get more disordered, entropy increases. Psychological, we remember the past, not the future. And cosmological, the universe is expanding.
And he argues our sense of time, the psychological arrow, is tied to the thermodynamic one, because memory itself requires energy and increases overall disorder.
That's the idea. He then wonders about a contracting universe. If the cosmological arrow reversed, would the thermodynamic one? Would broken cups reassemble themselves? Probably not.
His no-boundary proposal suggests that even if the universe eventually contracts, a well-defined thermodynamic arrow increasing disorder might only exist during the expanding phase.
And he uses the weak anthropic principle again. Intelligent beings like us can only exist and make observations in a phase where these arrows line up, like they do now.
So we experience time flowing forward because that's the only kind of universe phase that allows for beings complex enough to experience time at all. Interesting loop.
Very much so. Chapter 10 gets more speculative. Wormholes and time travel.
The sci-fi stuff.
Yeah.
He mentions Gödel found solutions to Einstein's equations that technically allow time travel loops in a rotating universe.
And Einstein-Rosen bridges, wormholes, theoretical tunnels through space-time.
Could connect for distant places or even different times.
Theoretically, yes, but the big problem is stability. These things would likely collapse instantly.
Unless you had some kind of exotic matter. with negative energy density.
Right. Something that violates normal energy conditions in general relativity. We've never observed anything like it, and that might be fundamentally impossible.
So the consensus is still pretty much no faster than light travel, no going back in time.
Yeah, as far as we understand physics now, those doors seem firmly closed. Fun to think about there.
Absolutely. Okay, finally, Chapter 11, the unification of physics. Back to the big quest.
Trying to reconcile quantum mechanics and general relativity. The theory of quantum gravity.
Hawking was hopeful, right? Cautiously optimistic. He talks about superstring theory as a possibility.
Which was very prominent then. The idea that particles aren't points, but tiny vibrating strings in, like, 10 dimensions.
10 dimensions, what happens to the other 6 we don't see?
Supposedly curled up incredibly small. But string theory, as the entry notes, was and still is incomplete, hard to test. It's not the final answer yet, if it ever will be.
He lays out possibilities. Maybe we will find a complete theory. Maybe it'll just be better and better approximations. Or maybe there is no single ultimate theory.
Limited, perhaps, by the uncertainty principle itself.
But he hoped studying the very early universe, where both gravity and quantum effects were crucial, might hold the key, maybe in the 21st century.
The jury's still out on that prediction, but the search definitely continues.
And in the conclusion, he brings it all together, humanity's journey to understand, from myths to math.
Recalling Laplace's determinism, but now filtered through quantum uncertainty.
And noting how cosmology shifted from philosophy and religion towards math and observation, creating a bit of a split.
But he ends with that incredible line, hoping we could achieve a complete understanding, because that would be the ultimate triumph of human reason, for then we would know the mind of God.
Such a powerful, almost mystical ending to a book grounded in physics. It really captures that deep yearning.
It really does. So, wrapping up this deep dive, A Brief History of Time was just monumental in bringing these huge cosmic ideas to, well, everyone.
Yeah, we've gone through the publication story, the big concepts, Big Bang, black holes, space, time, all of it.
Hopefully exploring these ideas gives you a new way to think about the universe, about reality, and maybe our own small place within it all.
And maybe leaves you with this thought. Science keeps moving, often in completely unexpected ways. What discoveries might be waiting out there? What new ways of seeing the universe might future generations have that even someone like Stephen Hawking couldn't have imagined?
It's an ongoing story, isn't it? And a fascinating one to be part of.